Welcome to the 10th and final installment of the probability portion of ProbStats. So we're going to talk about probability as area. So we're going to have infinite cardinality for our probability spaces. And we're also going to think of how to use continuous functions as probability density functions. So first, let's just ask a probability question that you could probably solve without any help from me, but we'll just make it clear that we talk about, our probability formula talks about the cardinality of A and the cardinality of the probability space. Well, here we have a triangle DOG, and so our probability space is just the triangle. All right, so what's the probability of an event? Well, a probability of the event is going to be some area in the triangle. For example, what is the probability that y is less than 1? Right? If I pick a point at random from the interior of the triangle, what's the probability that its y coordinate is less than 1? Well, all of the points with y coordinates less than 1 are below this horizontal line here, so we're talking about this area. And so that's what we mean when we talk about probabilities. By the way, this point here occurs at 2/3, right? It's 2/3 of the way along. And so we can do this area. Actually, it's easier to calculate the area of the upper triangle and subtract from 1. So it turns out that the area that we're talking about is 5/6. And again, here's the intersection point. So you can calculate this triangular area, which has height 2, and its base is 2/3. And any way you go, you're going to get 5/6. Okay, so then for part B, what is the probability that the y coordinate is greater than the x coordinate? Well, I'm going to draw the line y equals x, right? And this coordinate, this point is 3/4, 3/4. So that means that the height of this triangle is that dotted line I just drew, and it's 3/4. So I have 1/2 3/4 times 1, so that's where the 3/8 comes from. The 1/2 of 3/4 times 1 divided by the 3/2, which is the area of the probability space. So when you do that math, you get an area of 1/4. And finally, what is the probability that y equals 1? So that's interesting. Now we're just saying, hey, what if I draw this line and I pick a point in the interior? What's the probability that it lands on the line I drew here, that it lands on the line y equals 1? And this is an important concept to get. The probability of landing on a one-dimensional figure, if I'm drawing from the interior of a two-dimensional figure, is equal to 0. This line has no mass, right? There are infinitely many lines in here, all of which have uncountably infinite amount of points. So actually the probability is 0. So same thing if I was drawing from the interior of a square, which was inside of a sphere, right? A two-dimensional figure has 0 mass in three-dimensional space. So that's how probability as an area works. Let's consider what it would take for a continuous function f of x to be a probability density function. And the first thing I want to remind you of is some calculus, right? So when we were defining the integral, we started with a summation, right? We were adding up these rectangles, adding up the area of these rectangles in a summation, and then we took the limit. When we take the limit, right, we get the integral. Well, the same thing is happening. Our PDFs or the expected values of our PDFs are just the sums of these probabilities, right? We have, or if we think of summing up all the probabilities, that it'll be equal to 1. Well, now instead of a summation, we're going to have an integral. So for discrete PDFs, we sum them up sum up all the probabilities, that's equal to 1. For a continuous PDF, we're going to use the area under the curve. Must be equal to 1 criteria. And again, it just relates back to how the integral was defined in basic calculus. So if you recall, we said that a discrete probability density function had to have these properties. All the individual probabilities had to be 0 or greater. None of the probabilities could be greater than 1. No matter what your high school ball coach said, you can't give more than 100%, right? With probabilities, they're between 0 and 1, inclusive of the 0 and the 1. And the sum for all possible outcomes in X, the sum of the probabilities add up to 1. Okay, so we can define probability density functions based on continuous functions. We'll have the same thing. The function has to be positive. All function values have to be, non-negative, I suppose I should have said for clarity. The function values can be equal to 0, and they can be positive, but they can never be negative for all real numbers. And the function has to be finite. And so it has to be bounded. It can't go to infinity. If it has a vertical asymptote, and it blows up to positive infinity or negative infinity, actually, right? Because then we'd violate this one. But we can't have a vertical asymptote in the middle of our function. So for all reals, it has to be defined and finite. And finally, we're going to require that the area under the curve equals 1. And if we have a function like this, a function f of x like this, then it can serve as a probability density function. Now, I do want to make the point that this section is not going to be tested very much. I might put an area probability problem on your test or exam, but I'm not going to have these integrals. So calculus 1 is the prerequisite for this course, and some of these infinite integrals that's required to really do this section in depth and rigor aren't part of the prereqs. Most students won't see that until possibly Calc 3. So I'm going to show you a Calc 1 level integral. But this is not a very interesting probability density function. I have some examples later of some important ones, but again, we don't see the calculus that we need to do them until much later. So this section is just a brief overview. So let's take a look at this. So we have the probability density function is k times x. But that's only true between 0 and 5. So if x is less than 0, then the function is identically 0. And if the function is greater than 5, if x is greater than 5, then the function is identically 0. So it only takes on a positive value between 0 and 5. Okay, so the first thing that we have to do is we have to determine the correct value for k. So let's go. Let's go here. Right, and so we have a function that looks like this, and somewhere out here is x equals 5. Okay, and the idea, we have this function y equals kx. The idea is we want to choose this k so that the area under this curve between 0 and 5, we want that area to be equal to 1. Now you could probably do this without calculus, but the point was kind of to show calculus. So we're going to we know that f of x equals kx. And so what we'd like to do is take the area under the curve between 0 and 5. So we're going to do the integral of f of x dx using the limits 0 to 5. I don't have to integrate below 0 because it's identically 0 down there. There's no area under the curve below 0, and there's no area under the curve above 5. So the only place where I'll have area under the curve is between 0 and 5. Well, this is the integral from 0 to 5 of kx dx, which is equal to kx squared over 2, evaluated at the endpoints 5 and 0. And so I have k times, right, this is 25 over 2 minus 0. And so we know that the area under the curve is 25k over 2. Now what we want to do is we want to set this equal to 0. It's not, set it equal to 1. It's not equal to 1, but the whole point was to figure out what k needs to be. So if we set this equal to 1, then we can solve for k, and we find out that k must equal 2/25. All right, so now we have a probability density function. So our PDF is f of x equals 2x over 25. And that will satisfy the rules that we were given, right? If we go back up here and we look at the rules, right? Our continuous PDF is definitely greater than or equal to 0, right? We're putting in positive numbers, and 2x. If x is positive, 2x will be positive. Divide it by positive 25, it still stays positive. It's certainly bounded. It's just that line with slope 2/25 that goes through the origin. And then we calculated this area, and we chose k equals 2 over 25 to make sure that this is true. So now we have a proper probability density function. And so we can answer questions like the following. How do I figure out what the probability if I draw at random from the area under this curve, right? So it's this triangle that we drew that we're asking about. We're saying if we draw a point at random from this green shaded area, what's the probability that the point I draw has an x coordinate that is 2 or less? Probability that x is less than 2. Okay. So let's jump back. And we have our function. So now the probability that x is less than 2 is going to be equal to the area under the curve between 0 and 2. So this is going to be 2x over 25 dx. And we can pull the constant out in front. So I'm going to have 2 over 25 times, so I'm going to do this integral. So the 2 over 25 is out front. So this is just x squared over 2 is my integral, my indefinite integral. Then I'm going to add my limits of 2 and 0. So I have 2/25 times 4 over 2 minus 0. So this is 2/25 times 2, which is equal to 4/25. So that's the probability calculation we just do and integral. And I'm going to kind of deviate from what the slides were showing on purpose, because I want to show you how the expected value works. So for a discrete probability density function, right, we were taking the expected value as the sum of x times p of x. Well, for a continuous function, f of x, then the expected value of this continuous random variable x is going to be the integral across all real numbers of x times f of x dx. And the same thing when I need to calculate the variance, then I'll be calculating the expected value of x squared, right? And so I'll have an x squared here. So I can do the same thing as I did with the summations and use the same exact formulas. It's just all my summations switch to integrals. Okay. So, but again, you won't have to do this. I'm showing you this more for the people who go on and take a stats minor. The next course that you would take is stochastic processes, which is Prob Stats 3360. Excuse me, that's Math 3360 stochastic processes, and that's one of the things you would learn in that course is how to do all of this information. It has different prereqs, so that's more suitable. But still, I can show you this one. This is all Calc 1 stuff. So to calculate this expected value, right, so when we have f of x equals 2/25 x, then I can calculate the expected value by taking the integral. Again, I'm not going to worry about minus infinity to positive infinity. I'm going to worry about 0 to 5 because we know we're not going to have any area under the curve less than 0 or when x is greater than 5. So this is, I'm going to put my 2/25 out front. And so I'm actually doing the derivative of x squared dx. Why? Well, when I pull this out front, I just have the x left in here, right? When the 2/25 comes out front, my function is just x, but then I'm multiplying by this x, which is why I have the x squared. Okay, so I can calculate this. I just have 2/25 times x cubed over 3 evaluated at 0 and 5. And of course, 5 is the one that's important because when I plug in 0, this will be 0. So this is equal to 2/25 times 125 over 3, which I believe simplifies to 10/3. Now this makes sense, 3 1/3. Let's just scroll back up here. And what we're saying is, what this means is that if I'm picking random points inside this green shaded area, then I just say I do this hundreds and hundreds of times, and then I take the average of all the x coordinates of the points that I've drawn, then the average or expected value is going to be 10/3, which is about 3 1/3. And it makes sense, to me at least, because it's going to be closer to the 5 than it is to the 0 because the weighting is heavier on the right. There's more points to be drawn over here on the right than there are over here on the left. So the expected value or the average x value is 3 1/3. Again, this is all I have to show you. I just wanted you to have an opportunity to see how this works, and it will be helpful going forward if you take another course. Also, hopefully this helps you understand some of the formulas in statistics. For example, the normal distribution is a, oh, and I put, this should be an x. Sorry, change that in your notes. So this is the normal distribution. And if a normal distribution has an average of mu and a standard deviation of sigma, then its PDF is this one. Okay. I'm not going to go too deep into that. We'll talk about this a little bit more in statistics. One thing you should notice if you remember any calculus at all, if we think about what values if we get to pick any values for mu and sigma, to make our lives easier with the mathematical computations, what should they be? What should I pick for mu and sigma? And if you give that, a few moments of thought, you'll figure out why the standard normal chose these particular values. And that's the standard normal is the particular version of the normal distribution that we use for calculation purposes. And I will mention one other. This is another very, very common continuous PDF. G of x equals lambda. Lambda is just some real number. Lambda e to the lambda x, and of course the reason there's a lambda here and a lambda here, if you think about taking the, if you think about integrating, we need this one here to make things balance out when we take the integral. So the exponential distribution is related to the two Poisson processes, which is a big one in stochastic processes, and the Poisson distribution. And it's also the continuous analog of the geometric distribution. So it's an important one, and you would get exposed to this in any probability course that went any further than we're going, right? You would get exposed to this. But again, the prerequisite for this course is Calculus 1. So I've kept this entire presentation at a Calc 1 level. To do the integrals that are required here are higher than Calc 1. So this is the final installment of the probability portion. So congratulations for making it this far, and I'll see you in a little bit with the first statistics video. Remember to do the content quiz, the completion quiz. Good luck.